Hello students, today we will see moment of inertia of circular disc. First case, the moment of inertia of circular disc about an axis passing through the center perpendicular to the plane of the disc. That means this is the disc you can see here, and an axis you will see. This is passing through the center of the circular disc and which is perpendicular to the plane of the disc. Okay, now we'll see to find out the moment of inertia about this axis. This is in y axis, as you can see here, y dash I have written here. Okay, so to find out this, we have taken an element, that means a small ring like structure you are looking here, that we will take as an element, and which is x distance from the rotational axis, that is y dash, and the radius of the circular disc is r, capital R. It is the thickness of this ring is dx. So this is the thickness is dx. Okay, now we will see, first of all we will just take out the moment of inertia of this ring, and then we'll extend this from 0 to r. That means this ring should be spread like this way from 0 to r, and that will become the circular disc. So we will integrate the moment of inertia of this ring from 0 to r. Okay, so we will find out the moment of inertia of circular disc about this axis. For this, first of all, we have taken here total mass of the disc, as always we are taking capital M. Area of the disc is pi r square, and if we'll take out mass per unit area, that will be equal to m upon pi r square, that is mass per unit area. Now we will take out this moment of inertia of this ring. So for that we required the area of this ring also. If you cut this ring from here and then you will just open it, it will become the rectangular strip. This ring will become like this rectangular strip, and as I told you, the thickness of this ring is dx. So the width of this rectangle strip is dx, and because it is x distance from this rotational axis, so obviously the length of the ring will be 2 pi x, which is the circumference of the ring. And this ring which we have taken here, that is a very thin ring, that is dx is very small, that's why we have taken the dx it. Okay, so that means there is no issue of this x, and this outer circular circumference, there will be no difference, means a slight difference you can say will be there. So directly we can take the strips here, and this strip is the length of the strip is 2 pi x and the width is dx. So if you find out the area of this element, the area of the element, because it is a rectangle, that will be length into width, and the length is what, this is 2 pi x, and the width is what here, dx. Okay, so area of the element will become now 2 pi x dx. Now if we will take out the mass of the element, so it will be what, mass of the element. So it is the mass per unit length, that is m pi r square, and the area of the element, that is 2 pi x dx. Okay, this is 2 pi x dx. Now the mass of the element will become here, pi would be cancelled, this is 2m x dx upon here r square. Okay, so this will be the mass of the element, and which we can write as dm. Now we will take out the moment of inertia of element. So the moment, so we will see here the moment of inertia of element, inertia of element moment of inertia of element will be, this is dm multiply with the distance, perpendicular distance from the rotational axis, so square of that, and this will be equal to what? The dm multiply with x square. Now dm is what here? Dm we have calculated, that is the mass of the element, 2m x dx upon r square, and this is x square, so it will become here, that is 2m x cube dx upon r square. Okay, now this moment of inertia of this element we will integrate from 0 to r, as I told you. So we will get the moment of inertia of this circular disc. So for that, the moment of inertia of circular disc this will be equal to integration 0 to r of the moment of inertia of the element, that is 2m x cube r square. Now we will see here this quantity m and r are constant, and 2 is also constant, so it will come out from the integration sign 2m r square, and the integration of x cube dx. So the integration of x cube with respect to this dx, that will be equal to, this is x to the power 4, just we'll apply the formula, x to the power n dx, that is x to the power n plus 1 upon n plus 1, so 3 plus 1, that is 4, and here also it is 4, and we'll see now the upper limit r and the lower limit 0. Now what we will find here, you can see that this is the moment of inertia about the axis. So this I am just writing as IC here. I am writing this as IC, and now we will apply the upper limit and the lower limit. So this is 2m upon r square. Upper limit is r, so r to the power 4 upon 4, and the lower limit is 0 here, so this will be 0 here, and so the value will come here, r to the power 4 upon 4. So simply you will find this is IC is equal to 2m upon r square, and this is r to the power 4 upon 4. If we simplify, 2 ones are 2 twos are, this will be cancelled, r square and r square will be cancelled. So the IC will become now, IC, that is the moment of inertia, will become now the mr square upon 2, mr square upon 2. So this will be the moment of inertia of a circular disc about an axis passing through center perpendicular to the plane of the disc. We will see the second case of moment of inertia of circular disc about one of the diameter. You will see that this is a circular disc, and the two diameters we have taken here, that is AB and CD. AB if you can consider x-axis, and CD if you can consider z-axis. And this is, you know already, that we have taken the axis which is passing through the center of the disc and perpendicular to the plane of the disc. Plane of the disc is in the plane x and z, and this is y axis. So now you will see here that this diameters are perpendicular to this axis y dash. Okay, so here we can apply the theorem of perpendicular axis. So we'll write here, according to theorem of perpendicular axis, theorem of perpendicular axis, that is the IC, this one y dash is what? It is IC, that means the moment of inertia of circular disc about an axis passing through the center, and it is perpendicular to the plane of disc also. Okay, so this is IC, and it can be sum of IAB plus ICD. Now we'll see here, because this is IC and IAB is a diameter, AB is a diameter, so we can write this ID, and this is also we can write as ID, because this is the moment of inertia about one of the diameter, and this is also moment of inertia about one of the diameter. Both the diameters are equal because both are of having the same means both are diameters of the same disc. Okay, so this will be ID and this will be ID. Then IC, we have already calculated the moment of inertia about an axis passing through center. Already we have calculated, that is equal to mr square upon 2. Okay, so we'll put this value here. This is mr square upon 2. Now this will be 2ID. Here we'll take ID this side, so this is ID mr square, and this 2 will go there, that is this will be equal to 4. So now we'll find out the moment of inertia of a circular disc about one of the diameter, and that is equal to ID mr square upon 4, mr square upon 4, and this is half of the moment of inertia of a circular ring about one of diameters. Okay, third case for the moment of inertia of circular disc about an axis passing tangentially parallel to the diameter. This is the diameter AB. We have taken one of the diameter, so this is the diameter AB, and an axis which is passing tangentially from this circular disc. See that, touching one point, tangentially it is passing, and it is parallel to this diameter, parallel to the diameter of the circular disc AB. Okay, so we have to find out the moment of inertia about this axis KL. So for that we can apply here the theorem of parallel axis. So according to theorem of parallel axis, the moment of inertia about KL must be equal to the moment of inertia about AB plus the whole mass of the circular disc, that is capital M, and the distance, perpendicular distance between this axis, that is mr square. The perpendicular distance is the radius, so this is mr square. Now we'll see here this IKL, moment of inertia about this axis which is passing tangentially and parallel to the diameter, is equal to ID, AB is a diameter, so I am writing it ID mr square, and ID we have calculated already, that is the moment of inertia about one of the diameters. So this ID we have calculated in the previous section, that is mr square upon 4. So it is mr square upon 4 and plus mr square. We'll take LCM here and this will be equal to 5 mr square upon 4. So IKL now I will write, because it is parallel, so I am writing this sign parallel. Moment of inertia about moment of inertia of circular disc about an axis passing tangentially and parallel to the diameter is equal to 5 mr square upon 4. So this would be the formula here. The moment of inertia of circular disc about an axis tangentially perpendicular to diameter. This is the fourth case which we are looking here. This is the circular disc of radius r and mass m, capital M. AB is one of diameters, and this YY dash is an axis which is passing through the center of the circular disc and perpendicular to the plane of the disc. Here you will see this is an axis KL and it is passing tangentially, just touching the point B here, tangentially to the circular disc, and this is perpendicular to the diameter of AB. Now we'll find out the moment of inertia about this KL axis. Just to find out this, we'll apply here the theorem of parallel axis, and this time we'll take an axis. This is the axis which is perpendicular to the plane of the disc and passing through the center. So YY dash, this is KL is parallel to YY dash. So we'll write here according to theorem of parallel axis. We'll see here this IKL, moment of inertia about KL, must be equal to moment of inertia about YY dash, which we'll write as IC, because this we have considered the axis which is passing through center and perpendicular to the plane of disc, and we have denoted it before with the IC, plus total mass of the disc and the perpendicular distance between these two parallel axes, that is R, square of R, that is R square. Now this IKL is equal to IC. We have derived the formula for IC already, and this formula is IC equal to mr square upon 2. So this only we will apply here. The moment of inertia about an axis passing through center perpendicular to the plane of disc is equal to mr square upon 2 plus mr square. Now IKL is equal to, this is 2, will take LCM, the sum will come 3 mr square upon 2. Now IKL, this sign I am just changing here because it is a axis which is perpendicular to the diameter. So I'll just write the perpendicular sign here, that I perpendicular. So you will understand by this symbol that we are taking the moment of inertia about an axis which is passing tangentially perpendicular to the diameter, and this is equal to 3 mr square upon 2. So this will be the formula here for the moment of inertia about the axis passing through tangentially and perpendicular to one of the diameters. Moment of inertia of thin rod. Now we are calculating moment of inertia of thin rod. First case is that about an axis passing through center of thin rod and perpendicular to plane of the rod. you can see that this is a rod, that is thin rod. The length is very large. Comparison to the radius can be considered as the 2 dimension, that means the plane like structure. And you will see that the one axis is passing here perpendicular to the rod this way. This is at the center, okay. And so that this axis divide the rod in two equal parts, that is L by 2 and L by 2. If we are taking this side as L by 2, then this side we are taking like minus L by 2, okay. Now we will consider here the mass, total mass of the rod is capital M, and now we will consider an element here. You will see that this is a small element, the thickness of the element is dx, and this is x distance from the this rotational axis which we have considered here from the center of the rod, okay. So it is x distance. Now we are going to calculate the moment of inertia. For that what we required, first of all, the total mass of thin rod, this is equal to capital M. Now the total length is L, so we will see mass per unit length. Mass per unit length, this is equal to M upon L. Now for this element we will consider the mass. What will be the mass of the element? So we will see here the mass of the element is mass of the element, that is the mass per unit length, M upon L, and the thickness, that is into dx. So this is mass of the element, which we'll write as dm also. Then we'll take out the moment of inertia, and we know that moment of inertia of the element which we have chosen, that will be equal to mass, that is dm, multiplied with perpendicular square of the perpendicular distance, that is x square. So the distance is x and square of this perpendicular distance x square, okay. Now what we will do, we'll just integrate this the moment of inertia of the element from minus L by 2, means from this distance to this distance, okay. So that we will calculate the total moment of inertia of the total rod, that is about this axis y dash. So here we'll take out, this is moment of inertia of the rod is given by moment of inertia of the rod is given by, when we integrate this quantity dm into x square from minus L by 2 to L by 2 here. So this is integration, and this will be the IC, moment of inertia about the axis passing through the center. So minus L by 2, and dm is what here? Dm is m upon L into dx, and this is x square here. So IC will be equal to m and L is the constant quantity, and here the integration of x square will be x cube upon 3. The integration of x square, that is x cube upon 3. Now the upper limit and the lower limit. Here you will see the mass is constant, the length of the rod would be constant, and here x cube, that is in place of x cube we'll write first L upon 2 the whole cube upon 3 minus L upon 2 the whole cube upon 3 here. Okay, so this is L cube, and 2 2s are 4 2s are 8 multiplied with 3, that is 24. Here also the same thing would be there, the minus, this will come when we take cube, it will come minus only, and minus would be plus. So the quantity will come here, that is m upon L, and it is L cube upon 2 3s are, 2 8 3s are, that is 24, and minus plus it is L cube, this is also 24. So L cube upon 24 plus L cube upon 24 will give us, this will give us IC, it is equal to m upon L and L cube upon 12, L cube upon 12. Okay, so 1L would be cancelled, and the formula will come that IC is equal to ml square upon 12, ml square upon 12, and this will be the formula for the moment of inertia of the thin rod about an axis passing through the center of the rod and perpendicular to the plane of the rod. Moment of inertia of thin rod about an axis passes through one end of the rod. So this is the rod, this is an axis which is passing through the center and perpendicular to the length of the rod. This is the axis about which we have to find out the moment of inertia, and this is passing through the end of the rod, means one ends of the rod. Here you will see we can apply the theorem of parallel axis, because this KL axis is parallel to this axis YY dash. So here we can write according to theorem of parallel axis, this moment of inertia about axis KL must be equal to moment of inertia about the axis passing through the center of the rod and perpendicular to the length of the rod, which we have indicated already as IC, and plus the whole mass of the body and distance between these two parallel axes, that is L upon 2. So distance between these two parallel axes and square of it. So it will be like this. Now we have already calculated IC, that is ml square upon 12. So it is ml square upon 12 plus m, this is L square upon 4. Now we'll add it. When we add it, we will take the LCM 12, then this is ml square, and this will be 3ml square, that is 4ml square upon 12, and when we cancel it, 4 1s are 4 3s are, it will come moment of inertia about axis KL will be equal to the mass square of the length upon 3. So this is the moment of inertia about an axis which is passing through one end of the rod. Now we'll see whatever we have derived the moment of inertia for the circular disc, for the ring, or for the thin rod. This we will summarize in this tabular form. Other than this, some other geometrical figures are there. We will see the axis of rotation and the moment of inertia, radius of gyration of other body also, other system also. So the derivation of these systems are not in our syllabus, means the derivation is not there, but we are using the moment of inertia and the radius of gyration of these bodies. Okay, so first of all, look at here. This is thin uniform circular ring. We have seen the 4 cases already. We have derived the formula also for the moment of inertia in all 4 cases. Okay, and this is about axis passing through center mr square, and radius of gyration will see that this is r. So whatever quantity is given here in the moment of inertia, if you just separate m from that quantity and take the square root, you will get the radius of gyration. For example, you will see here mr square is the moment of inertia. Just separate mass from here, so the quantity remain is r square. If you take the square root of r square, you will get r, and that will be the radius of gyration. This is in diametrical position, thin uniform circular ring. If axis is one of the diameter, in such situation we got the moment of inertia mr square upon 2, and here also if you just separate m, the remaining quantity is r square upon 2, and if you take the square root of this quantity r square upon 2, you will get r upon root 2, and that will be the radius of gyration. Same, the third case we have seen, tangentially parallel to the diameter, that is 3mr square upon 2, and the radius of gyration is r root 3 upon 2. Now I think no need to explain this also. Just separate m, and whatever quantity will left, take the square root of this, you will get the radius of gyration. Okay, tangentially perpendicular to the diameter, the moment of inertia is 2mr square, and the radius of gyration is r root 2. Now for the uniform circular disc, these 4 cases already we have derived. About axis passing through center is mr square upon 2 and r upon root 2. Diametrically, or about one of the diameter, you can say, that is the moment of inertia is mr square upon 4 for the uniform circular disc, and the radius of gyration will be r upon 2. Tangentially parallel to the diameter, that will be 5 mr square upon 4, and the radius of gyration is r root 5 upon 2. Now tangentially perpendicular to diameter, the moment of inertia is 3mr square upon 2, the radius of gyration is r root 3 upon 2. For the thin rod also, 2 cases we have seen, and for the 2 cases, that is passing through center and perpendicular to the length of the rod, that is ml square upon 12, and the radius of gyration will be L upon root 12. Here for thin rod, thin uniform rod, which the axis is perpendicular to the length and passing through one end, in such situation the moment of inertia is ml square upon 3, and the radius of gyration is L upon root 3. Now till here we have derived the formula which was there in the syllabus also, but this plain lamina uniform rectangular bar, this is not in the syllabus, means the derivation is not in the syllabus, but we will use the formula for the moment of inertia and the radius of gyration. And for this plain lamina uniform rectangular bar, that is one case is there passing through center perpendicular to the length and the width. Okay, the lamina will be like this type of lamina will be there, and we are just we'll get this is this way, the from the center and perpendicular to the length and the width of the lamina. Okay, so the moment of inertia will be m upon 12 L square plus B square. the radius of gyration is root of L square plus B square upon 12. For the uniform solid cylinder, about axis of cylinder, so this is mr square upon 2 and the radius of gyration is r upon root 2. Axis of cylinder means this is uniform solid cylinder. This type of uniform solid cylinder is there. So about axis, if you will see, this will be like this. This is which is passing through the axis of the cylinder. Okay. Now axis passing through the center perpendicular to the length. That means this way, perpendicular to the length, this axis. Okay. Here we will see m r square upon 4 plus L square upon 12 and the radius of gyration is root of r square upon 4 plus L square upon 12. For the uniform hollow cylinder, the same way the cylinder would be there as we have taken the solid cylinder, but it is hollow. Okay. So structure will be like this only and the axis also will be taken like this only. The first one is the about axis of cylinder like this. Okay. And moment of inertia will be mr square. The radius of gyration is r. Now for the second case, passing through center perpendicular to the length, this type of axis will be there perpendicular to the length, and for this the moment of inertia will be m r square upon 2 plus L square upon 12 and the radius of gyration is root of r square upon 2 plus L square upon 12. Now the next figure we will see here, this is the uniform solid sphere. For a uniform solid sphere, about diameter, the moment of inertia would be 2 mr square upon 5 and the radius of gyration r root 2 upon 5. And for the second case, tangentially, if the axis would be there, so the moment of inertia is 7 upon 5 mr square and the radius of gyration is r root upon 7 upon 5. For uniform thin spherical shell, that means this type of it is a hollow sphere, you can consider. Okay. So about diameter, it is 2 upon 3 mr square and r root 2 upon 3 will be the radius of gyration. For this, tangentially, you will see here, tangentially the axis would be tangentially from this uniform thin spherical shell. So the moment of inertia is 5 upon 3 mr square and the radius of gyration is r root 5 upon 3.